In this lecture, we shall be talking about physical unclonable function or PUF. We mentioned earlier that this physical unclonable function plays a big role in designing systems in terms of hardware such that it becomes secure. Means in other words, with respect to hardware security, this physical unclonable function or PUF can be used to design secure systems in a relatively easier way. So, let us see what this PUF is actually all about. In this lecture, we shall first be talking about the basic concepts of physical unclonable function, then some applications of PUF and how they can be implemented. Okay. Talking about what is a physical unclonable function, you can say it is some kind of a fingerprint of some device. Now, how do we define a fingerprint? Suppose as a human being, my fingerprint is something which is supposed to identify me. My fingerprint is supposed to be unique. So, in the same way, whenever I design some hardware circuit and IC chip, the idea is there must be something which should be unique to that IC chip. It can be acting as a some kind of a fingerprint of that particular device. So, PUF is something like that, the concept is that it is defined as the fingerprint of some kind of a device. Suppose I have this kind of a PUF and we define something called challenge response mechanism. The way a PUF works is that suppose I can have a chip, and inside my chip the PUF can be sitting in between, this can be my PUF. Okay. Now, the idea is that when you use a PUF, there is a concept of a challenge and response pair or challenge response mechanism that comes into the picture. The idea is, suppose I feed a challenge C, this is some data I feed as input, I call it as a challenge, and I get an output which I call it as a response R. The C and R is referred to as the challenge response pair. Okay. So, this PUF defines a mapping between this challenge and this response, and the idea is that this PUF is something for which the challenge response pair is unique. If I design another IC chip where maybe the same kind of a PUF I am building, but for that PUF the challenge response properties will be different. So, challenge response will be something like a fingerprint of that particular device. Okay. So, this is something which we define as unclonable, it cannot be copied, it cannot be cloned, and instance specific, it is specific to that particular chip. The way it is implemented, this depends on manufacturing process variations. When multiple chips are fabricated, there will always be small variations here and there, no two things can be exactly identical. Okay. So, that process variations, device variations, that is what is exploited in the design of this PUF. Okay. Some of the desirable properties of PUF are mentioned here. These are quite obvious. First is it should be something which should not be too difficult to evaluate in terms of the challenge response. Suppose I give a challenge X, the response Y should be easy to calculate, easy to compute. Okay. It should be easy to evaluate. Secondly, for a particular device, the challenge response properties should be unique. The value of PUF X for a particular X will contain some information about the identity of the physical entity. That means, if I talk about a particular chip, there is a PUF here, whatever X I feed here, the PUF of X, if I call it Y, so whatever value I get Y, this should uniquely identify this IC chip. Okay. This should provide as the identity, and in the previous slide we already mentioned there is a concept of unclonable, means given one puff implementation, that means one chip, I have a puff inside. If I have another copy of the same chip, there is also the same kind of a puff, but the two puffs will never be identical. One puff, let us call it PUF, other puff, let us call it PUF dash. They will always be unequal, means for some given challenge, if you compute the response for the first one, compute the response for the second one, they will not be equal. So, it is hard to construct two puffs which are not the same, such that for the same value of x, their response will be the same. Okay. Their response will be different, that is the idea. And it is a one way function, that from y, from x you should get y, but given y you should not be able to get back x. It is quite similar to hash function calculations. The reverse mapping should be difficult. Okay. Let us take a simple example of an SR latch. I will just try to explain what this fabrication dependent or device dependent variations mean. Well, if you recall, for those of you know how an SR flip flop works, this is a single bit storage. We store one bit of information. Okay. There is one input in, that same input is fed to this S and R, let us say. This S and R are two different inputs, but let us assume that the same input value in is fed to both S and R. Now, let us say I apply 1 to input. If I apply a 1 here, then the output of this NOT gates will be 0, this will be 0, these are NAND gates. So, one input 0 means the outputs will be 1, both the outputs will be 1, both y and y prime will be 1. Okay. Now, let us say this in was 1, now I make it 0, I change it to 0. So, at this point in time both y and y prime were 1 and 1. So, as soon as I make it 0, these outputs of the NOT gates will both become 1, this will become 1, this will also become 1. Now, here something happens. You see, these are two gates. Now, two gates are fabricated in the chip. The two gates can never be exactly identical. Suppose this gate is a little faster, let us call it F. This gate is a little slower, let us call it S. This gate faster means when this is 1, so both the inputs are 1 and 1, 1 and 1 NAND output is 0. So, this output will be changing to 0 first, because this gate is faster. This gate is slower, so this output is still not 0. So, this will become 0 first, and this 0 will be fed back, 0 and 1, this will remain as 1. But if it were the other way around, then this would have become 0, this would have become 1. So, this output y, whether it will finally become 1 or 0, it depends on the relative delays of the two gates, which you cannot predict beforehand. So, here there is a source of randomness, it depends on fabrication. Okay. This is the basic idea behind which this kind of puff design we are trying to build. Okay. Fine. Now, from theory to practice, usually these puffs today, the most of the research papers, if you see, people have tried to build these puffs around field programmable gate arrays or FPGAs. Many security protocols and implementations are based on FPGAs, and people have also implemented puffs inside FPGAs. Now, the advantage of FPGA is obvious. You can create a design and burn it on FPGA in your lab in house. You can program it, you can change the design whenever you want, but you should need to implement carefully when the implementation of a puff is required. Okay. See, for a particular implementation there may not be any non-determinism, like say you again look at that SR flip flop, that same SNR, this kind of a flip flop is there. Suppose in an FPGA implementation I design it in such a way that these two gates are placed in two different places in the chip. Let us say one gate is placed here, one gate is placed here, and these two interconnecting lines, their lengths may not be same, one may be like this, one may be like this. So, one interconnection may be longer, which means its delay will be longer. So, if this delay is longer, so that longer path can be the slower of the two, the other path will be faster. So, it depends on the layout, the way you connect, place the two gates and connect them, that which gate effectively will be faster, which will be slower, and whether the output finally in the example we took, whether it will be finally settling to 0 or to 1, right. So, this depends, you will have to understand that. Now, if you look at a chip, here I am looking at an FPGA chip. So, these are the different grids. Let us assume that the NAND gate that I was talking about, that NAND gate I can potentially place in any of the grids. I can place it here, I can place it here, I can place it here. Let us say I can place it here, I can place it here, I can place it here, so many places. Now, it depends where we are placing. Depending on that, some of them, if I set the input to 1 and then to 0 just in the previous example, some of them will be settling down to 0, some of them will be settling down to 1. So, accordingly what will be the final values of y's, that will depend on how you are interconnecting them. So, it does not depend on the circuit, but rather on how you are making the interconnection, where you are placing which gate. So, in FPGA particularly, here you are not fabricating anything, you are mapping a design into a programmable fabric. So, where you are mapping, how are you interconnecting, that will depend, that will determine what will be your final challenge response pair of that puff in terms of the SR flip flop that we have just now talked about, right. So, the difference in the routing delays of these paths will determine that whether the flip flop output will be settling to 0 or 1. So, and that will depend on in which location you are placing the flip flop, the xy coordinates, right. Okay. So, talking about the advantages of puff, if you talk about puff as a basic building block you are using to design secure hardware, there are broadly two things. It reduces the cost of secure implementation, it also increases the security. Now, here I am showing two things. If there were no puff, then trusted party embeds and tests secret keys in a secure non-volatile memory. This is the typical thing which is done. Inside the chip, some secret value is stored in a non-volatile memory that is used for encryption decryption. There is some kind of a flash memory EEPROM, and adversary or an attacker can physically extract through side channel attacks. But if you have a puff, then some properties of the device that can be used to generate the secret key, and the key will never be stored anywhere, the key will never come out of the IC chip. Depending on the intrinsic property of some delays inside the chip, the key value will be automatically generated, okay? And the key is automatically deleted after its use, it is not stored anywhere. This is the advantage. There is another application of puff where you want to identify, like I have fabricated or I have designed a device and someone has made a clone or a copy of my device. I want to find out which is the original and which is the copy. You see, for the authentic device which I had designed, I know what was my challenge response properties. Let us say I have already created a table like that. This is the, for this challenge, this will be the response, for this challenge, this will be the response. Now, if some other device is given to me which contains a very similar puff, I can consult that same table, I can apply these challenges and see what the responses are coming, and I can compare whether they are equal or not, same or not, and if they are not same, we can reject the IC saying that this is not the same device. In this way, you can identify a unique device. Okay. Sometimes it is required, you need to identify a particular copy of an IC. You can use this kind of puff IC fingerprinting for doing that. Okay. There is another important application in public key cryptography. You can use puff to generate public and private keys on chip. You need not have to rely on a trusted third party to generate the public private key pair and deliver it to you through some mechanism. You can do it on chip. Okay. The idea is like this. Suppose you have a puff. So, whenever you apply some input to a puff, the response can be considered to be a random number. Response is random, it depends on the intrinsic properties of the device. It varies from one device to another. So, it is truly random. So, that random can be used as the initial value or the seed of a key generation, and this puff is typically used in conjunction with some public key algorithms. Typically in hardware we use elliptic curve cryptography or ECC. So, ECC and puff are sometimes used hand in hand, they are used together, and this with this ECC and puff we can generate a random seed through which the key generation module that can be inside the chip, that can be generating the public key which can be distributed outside, but the private key will never leave the chip, it will remain inside. Okay. You are not storing anywhere, and this private key can be generated online, you need not store it anywhere, and the public key also can be generated or endorsed anytime you want. You can again use that puff to apply a particular challenge, get a response, the key generation module will be generating the same public key. So, the manufacturer need not store any secret key value inside the chip, that will automatically generated by the puff mechanism, stored and generated by the chip itself, right. So, this is how it works, and in terms of cryptography it helps a lot. It saves a lot of time and effort to manage the key, to secure the key inside the chip, all right. Fine. Now, in terms of the practical design, how the puffs are actually implemented? Well, we are interested in chips, right. So, we are interested in silicon puff circuits which are implemented in silicon or CMOS. Okay. Now, as I said, the basic idea is that when you fabricate chips, there will be process variations, from one chip to the other there will be some variations. So, those variations are exploited here. But with respect to design, when circuit design is carried out, this process variation is a drawback. We try to make the variation as small as possible, but here the process variation is something which we are taking advantage of. We are trying to exploit the process variation and use it to our advantage, right. So, this is quite useful for puff design, and a number of research papers and a number of efforts have been carried out. Various puff designs have been explored. Some of them I am just briefly talking about. This is a very common and popular design. This is called arbiter puff. Schematically it is shown like this. You see these boxes, you can see rectangular boxes, these are nothing but path swapping switch. What it is actually is like this. Suppose there are two inputs, let us say A and B, there are two outputs, either these inputs will be coming out as it is or they will be interchanged, A will come here, B will come here, and what will happen, that will be dependent on a control signal. So, depending on this control signal whether it is 0 or 1, either the inputs will be coming out straight or it will be exchanged, right. Okay. Now, here what is happening? You see, at the input we are applying a pulse, let us say 0 to 1 we are applying, and this control signal combination, this is our challenge. We are applying some random bit pattern as a challenge 0 1 1 0 1 0 1 1 something. So, depending on that, some random path is getting selected, some of them are going straight, some of them are getting exchanged. So, the delays are different. So, when it reaches a final D flip flop, the delay can vary, that means which inputs will reach first. Here you see the same signal was fed to both of the inputs, but when it reaches here the two inputs may be different, may be little delayed with respect to each other, because they are following two different paths, the two paths are not identical. Okay. And the response we are storing in a D flip flop, one we are using as data, other we are using as clock. So, whatever we will be storing in the flip flop, that will be something unpredictable, it can be 0 or it can be 1, it depends on the relative delays of the flip flop. This is the basic principle behind arbiter puff. There will not be one, there will be many such puffs. So, the response will not be just one bit, there will be a multi-bit response, there will be many such units placed in the chip, in parallel it will go on. Okay. So, the same thing is mentioned here, there are n 2 port switching stages for an n bit challenge size. So, this will be actually n minus 1 not n, C0 to Cn minus 1. So, number of possible path for each of them, there will be 2 possible path, 2 into 2 into 2 into 2, it will be 2 to the power n. A particular challenge that you are feeding will be selecting a unique path, and accumulated delay as I had said is compared with a D flip flop, which is the arbiter circuit, which gives a 1 bit decision 0 or 1. If there are multiple such arbiter circuits, it can give a k bit decision, k bit response. Okay. Now, there is another kind of puff called ring oscillator puff. So, what is a ring oscillator puff? See, first let us understand what is a ring oscillator. If we take a inverter, the output I connect to the input, this acts as an oscillator. If I apply 0, output will be 1, 1 is fed back, again this 1 will become 0, 0 is fed back, again this 0 will become 1, 0 1 0 1 0 1, this will go on. The same thing will happen if any odd number of inverters are connected like this, let us say 3, and I am connecting, same thing will happen, but the delay will be a little more, 0 1 0 1 0 1, like this it will oscillate. Okay. This is called ring oscillator. Now, here the idea is that we have a number of ring oscillators. You see, you ignore this gates in the first stage, you see this NOT gates are there, and this NAND gate is also considered as a NOT gate. So, there are 3 inverter, let us say. So, there are a number of such ring oscillators in the circuit, right. So, the output is fed back here. Now, if it is enabled, if the enable line is 1, if we feed a 1 here, say a NAND gate with one of the input 1 is equivalent to a NOT gate. So, if enable is 1, then this becomes a NOT gate, it is a ring oscillator. If the enable is 0, then the output will be a steady 1, it will stop oscillating, right. This is how it works. Now, the idea is that there are so many ring oscillators, they are all oscillating. Okay. When oscillation means there will be some frequency of oscillation. So, what we do, using some challenge, we randomly select some ring oscillator. There will be several ring oscillator here, several ring oscillator here. Let us say there are 2 to the power n. Just using an n bit challenge, we select 2 ring oscillators, and their frequencies we measure in 2 counters. then we compare whether counter 1 is greater than counter 2 or not, which frequency is greater. This will be my final response. Okay. Now, depending on which ring oscillator you choose, these frequencies are different. So, the response will also get different, that means whether the frequency will be greater or less. Okay. This is how randomness is generated. Okay. This is how ring oscillator puff works. Then there is another kind of a puff which is based on static memory, random access memory, SRAM puff. This is a typical diagram of a MOS based static random access memory cell, 1-bit storage. Now, the idea is that when you switch on power to a chip, suppose there is such a memory cell, initially the memory cell can start with an initial value of 0 or a 1, but you do not know what. It will be either 0 or 1 depending on the manufacturer, which transistor is faster, which one will be switching first. That way the output will be either set to 0 or 1. So, if you have many such random access memory cells, depending on the manufacturing properties, they will be initialized to 0 or 1 randomly. This is the idea behind SRAM puff. The power of initial values of SRAM cells are used as response, and which cell you are selecting, that is the cell address, that will be the challenge. Randomly you select a cell, you see it is 0 or 1, randomly you select another cell, see it is 0 or 1, like that. Okay. So, for a particular manufactured chip, that should be the same, because for a particular property of this transistor devices, the way they are manufactured, their delays, their gains. So, when you switch on the power, it will be either 0 or 1, it will be deterministic, but across two chips it may be different. Okay. But this SRAM puff is more easy for an ASIC design, for a chip, for an ASIC chip, but for FPGA implementation, SRAM puff is very difficult, because in FPGA whenever you are initializing the power, all SRAM cells are reset to 0 by default, they are cleared. So, you cannot use this puff using SRAM for FPGAs. Okay. So, to summarize, this puffs are something which is very simple, do not need much hardware to implement. Nowadays, these circuits which I have shown, they are fairly simple, not much. So, they are relatively very inexpensive, and using puff you can make the security protocols that you are implementing in your chip much stronger. That is the basic idea, and if you do that, the kind of hardware based attacks we have been talking about, it becomes much more difficult to mount this kind of attacks. Your device becomes more secure. Okay. So, with this we come to the end of this lecture, where we talked about puff, physical unclonable function. In the next lecture, we shall be talking about hardware trojans, which are also very much related to hardware security we mentioned earlier. We shall be seeing it in the next lecture. Thank you.